Miss Wallace teaches chemistry.
Good day everyone. In this video I'm going to be doing calculations on heat of neutralization and heat of solution, and these calculations are my simple way of getting the calculations done. Alright, so just to recap, for heat of neutralization, remember neutralization deals with acids and bases. So the heat of neutralization is the heat change when 1 mole of water is produced from the reaction between an acid and a base. Right, and for the formula we're using, heat of neutralization is equal to Q over -1 times mole, where Q is equal to MCAT, M being the mass of the solution, so how heavy the overall solution when the acid and the base is mixed, how heavy that is, right? And then the mole is the mole of water, right? This is coming from the definition, so it's going to be the mole of water. Okay, now for heat of solution, when you think about solution, you think of solute and solvent, the solute dissolved in the solvent to make a solution, right? So the heat of solution is a heat change when 1 mole of a solute dissolves in a solvent, right? And just remember that the solute is the one that is being dissolved. It's oftentimes mass, right? Sometimes it can be a solid, a liquid, right, or a gas. But oftentimes in these calculations, you're going to see a solid version for the solute. Right, so it's the solute dissolved in the solvent. The heat change when 1 mole of the solute is dissolved in the solvent. For this calculation, we're using heat of solution equal Q over -1 mole, where Q is equal to MCAT. This time, the mass that we're using is the mass of the solvent, right? The mass of the solvent, how heavy the overall thing is, the mass of the solvent over, right here we can see the mole of the solute. This goes back to the definition, the mole of the solute. All right, so we have this question here: a 50 ml solution of 1.0 molarity. So 50 ml solution, just highlighting my values. 50 ml solution of 1.00 molarity HCl at 25 degrees Celsius is added to a 50 ml solution of 1 molarity NaOH at 25 degrees Celsius. After mixing, the temperature of the solution rises to 31.5 degrees Celsius. A says determine the heat of neutralization in kilojoules per mole. Note this, right, in kilojoules per mole. And B, draw the energy profile diagram for the reaction. Alright, so when we're doing this, it says determine the heat of neutralization in kJ per mole. Note that Q would have been kJ, right, over -1 times mole would have given us the mole, hence the unit. So the question itself is even telling us what we need to do, right? And this is heat of. How do I know what type of heat we're calculating for? So it says a 50 ml solution of this HCl is an acid, is added to NaOH, a base, so therefore we're solving for heat of neutralization as it would have stated in our question, right? So I wrote out the general formula. What's next is that I am going to be solving for Q. All right, so just remember that Q is equal to MCAT, and we're going to solve for all of these individually. Remember that M is going to be the mass, the total mass of the solution, right? And to get that, we're going to add the volumes. So it's going to be 50 ml of HCl plus 50 ml of NaOH, which gives us 100 ml. And remember that 100 ml is the same as 100 centimeters cubed, right? Now, how do we convert this volume to mass? Just remember that the assumption is that the density of water, my pen is not working, the density of water is 1 gram per centimeters cube, right? And if the overall volume of the solution is 100 centimeters cube, therefore the mass of the solution is 100 gram, and that's our mass. Next, we need to work for our specific heat capacity. We don't need to solve it, it's already known, so you can either choose to use 4.2 or 4.18. So I'm going to use 4.2 joules per gram per degree Celsius, And for changing temperature, it's going to be final temperature minus the initial temperature. Okay, so the final temperature that we got is said after mixing, the temperature of a solution rises to 31.5 degrees Celsius. So that would be our final temperature. The initial temperature, now note that we have to use the initial temperature of both of our substances, both the HCl and the NaOH, and we have to average it, right? So note that the initial temperature of HCl would have been 25 degrees Celsius, and the initial temperature of NaOH would also be 25 degrees Celsius. To average it, we divide it by 2 since it's two substances, right? And that would give us 31.5 degrees Celsius minus 25 degrees Celsius, which is equal to 6.5 degrees Celsius. So we would have worked out our Q. Note that Q, just a little highlight, Q is the amount of heat absorbed or released. So you might be asked to solve this. Q is the amount of heat absorbed or released, because sometimes you're asked to solve for this separately before solving for the heat of neutralization. Alright, so we would have worked out our Q. Now we're on to working out the mole part of the equation. So the mole, remember, it's going to be the mole of the water, right? Because remember, you know, heat of neutralization is the amount of heat that is evolved when 1 mole of water is produced from the reaction between an acid and a base. So it has to be the mole of water that we're looking at here. Right, and to get the mole of water, we don't know the mole of water. We weren't given a mass of water. So what we have to do, we're going to have to write out the equation. So first thing you do, write out your balanced equation. Right, that's the first thing you do, write the balanced equation. In this case, we had NaOH, which is aqueous, reacting with HCl, which is also aqueous, to give us NaCl AQ plus water. Just remember that our reactions between acids and bases give us salt and water, right? I took this, that's the salt that we formed, right? To balance this, note that we have 1 Na on the left, 1 on the right, 1 oxygen on the left, 1 on the right, 2 hydrogens on the left, H plus H, 2 hydrogens on the left in our reactant side, 2 hydrogens on the right, 1 Cl on the left, 1 Cl on the right. So this is balanced, right? And when we look at this, we can see that we would have had a 1-to-1 mole ratio to produce 1 mole of water, right? How I got the 1 is the coefficient in front. In chemistry, we call it the invisible one. The one, we're not seeing the 1, but it is there, right? So the 1 would have been here, a 1 here, 1 and 1. That's how I would have gotten the coefficient, all right? And I can choose any of these since I know their mole. I can calculate their mole. So it's going to be, I'm going to choose the NaOH. I'm going to solve for the mole of NaOH. Mole of NaOH would be equal to concentration times volume. And I'm using the general formula, mole is equal to con times volume. In other words, concentration is equal to mole over volume. Once you remember this equation, you remember the others. Right, so it's mole of NaOH equal concentration times volume. The concentration of NaOH that I would have gotten would be 1.00 molarity or mole per dm cube. The volume would be 50 ml. 50 ml or 50 centimeters cube is equal to 0.05 dm cube, right? Just divide it by 1,000 and we would get our dm cube. You must always convert to dm cube, right? So we're going to involve that in our equation, 0.05 dm cube, and so our answer, units will cancel, it's going to be 0.05 mole. And since it was a 1-to-1 mole ratio, so 1 mole of NaOH reacted with 1 mole of HCl to give us 1 mole of water, right? So therefore, since 0.05 mole of NaOH would have reacted, that means that we also would have produced 0.05 mole of water due to the fact that it's a 1-to-1 mole ratio. Right, so our mole of water is equal to 0.05 mole. And now we can solve for our heat of neutralization. So heat of neutralization, once again, heat of neutralization equal Q over -1 times mole, which is equal to our Q that we would have gotten, right? And we didn't even solve for the Q, right? So the Q, let me go back here. The Q is going to be the mass, which would be 100 grams times 4.2 joules per grams per degree Celsius times 6.5 degrees C divided by -1 times mole. And this should give us roughly 2.730 kilojoules when I work it out over -1 times the mole of water that we got would have been 0.05 mole. And so our answer is negative 54.34 kJ per mole. And the fact that we're seeing a negative sign suggests that this reaction is exothermic. And that's why I say use this formula with the negative, right? Even if it was endothermic, the negative would have cancelled and you would have gotten a positive value. So exothermic reactions, they have a negative enthalpy value, right? And another way that you could have looked at it is in the question, note that the temperature, it rose from 25, an average of 25 degrees to 31.5 degrees. And remember that for exothermic reactions, where heat is being released to the environment, and the temperature that we measure is the heat that was released to the environment, right? So that heat for exothermic reactions that was released, right, that's how we see our increase in temperature. All right, and guys, you could have looked at it this way, as notice that the average temperature initially was 25 degrees Celsius and it increased to 31.5 degrees Celsius. Once you see an increase in temperature, that increase in temperature is the increase in temperature of the environment, and the thermometer only measures the temperature of the environment. So therefore, once you see increase in temperature, it has to be an exothermic reaction. So from the get-go, we could have known that it would have been exothermic. Right, now the last thing to do is to draw my energy profile diagram. So my energy profile diagram, it's exothermic, and exothermic reactions, heat is being released, so we're losing heat. Once we're losing heat, it means that the products are going to have less energy than the reactants. So my reactants are going to be higher than my products, right? So reactants on the left, products on the right. In the case of reactants, we would have reacted HCl AQ plus NaOH AQ. Should have left a little bit more space, but and for the products, you would have formed NaCl AQ plus H2O liquid. All right. And now we need to complete the diagram. This would be the energy content on my axis, and the progress of the reaction. Alright, so we included the reactants and the products. These would be the reactants, products. Alright, I'm just going to label that here as well. Alright, so that's the first thing you do when you're drawing your energy profile diagram. You include your reactants and products. What's next is that we're going to have to draw our activation energy. Draw and label the activation energy. Alright, and activation energy, remember that it's the energy, the minimum amount of energy that the reactants need in order for them to break, to form new bonds. So it's going to go up, then come back down to our products. Alright, so the activation energy is going to be between the reactants and the highest peak right here. This is my activation energy. What's next is that you need to label your enthalpy change. Remember that the enthalpy change would have been the change between the reactants and the products, not the change between the activation energy and the products, but it's the energy change when the reactants form products. So it's gonna go from here to here, right? And we label it. So it would have been enthalpy neutralization equal negative 54.34 kilojoules per mole. And that's how we work out a heat of neutralization. Okay, now for this question, it says a volume of 50 centimeters cube of NaOH solution of concentration 1.0 mole per dm cube and temperature 26 degrees Celsius is added to 50 centimeters cube of sulfuric acid of concentration 0.5 mole per dm cube and temperature 27 degrees Celsius. After mixing a maximum temperature, note that they said maximum. So let's say you would have done this experiment and you carry it out, you realize that the temperature rose, it increased until it started to decrease again. It should be 3 until it started to decrease again, right? Well, we're going to be calculating our final temperature minus the initial. We're going to calculate our change in temperature. We're going to use the maximum temperature that was reached. That would give us our temperature change, right? So it's not the final temperature, but it's actually the maximum temperature that was reached, that would have been reached. Okay, and if it were endothermic reactions, it would have been the minimum temperature, the lowest temperature that would have been reached. All right, so let us work this out. Once again, we need to solve for the heat of neutralization, and we know that heat of neutralization is equal to Q over -1 times mole. Just remember that Q is the heat being absorbed or released, right? And for Q is equal to M cat MC delta T, and we're gonna work for our mass. So mass, remember that the mass is how heavy the solution is, and in this case we had 50 centimeters cube of NaOH reacting with 50 centimeters cube of HCl. This gives us a mass of 100 centimeters cube, not mass, volume, right? So it gives us a volume of 100 centimeters cube. We now need to convert this volume to mass, right? Using the density of water, which is 1 gram per centimeters cube for the density of water. So therefore, if 100 centimeters cube is present, therefore 100 gram is also present. We already know what our specific heat capacity is, 4.2 joules per gram per degree Celsius, and our temperature, or change in temperature, this time, as I said, even though we said final minus initial, we're going to use the maximum temperature that was reached, right? So I'm still going to use the formula final temp minus initial temp, but just know that I'm using the maximum temperature that was reached. In this case, the maximum temperature was 33.2 degrees Celsius minus the initial temperature. The initial temperature, note that we have two initial temperatures. So we have 26 degrees Celsius of our NaOH, and we have 27 degrees Celsius of our sulfuric acid. So to average this is going to be 26 degrees Celsius plus 27 degrees Celsius divided by 2. Therefore, my change in temperature is 33.2 degrees Celsius minus 26.5 degrees Celsius when I average, and so my answer is going to be, that gives us 6.7 degrees Celsius. Right, and we can just go ahead and work out what the overall value for Q is. That Q is equal to MC delta T. Mass is 100 grams. C is 4.2 joules per gram per degree Celsius. Change in temperature 6.7 degrees Celsius. This gives us 2,814. I cancel mass will cancel mass. It's degrees Celsius cancels degrees Celsius, and we're left back with just joules as the unit. To convert this to kilojoules, you divide by 1,000, and so we get 2.814 kg. What's next is that we need to work out the mole of water, right? And for the mole of water, we can choose to use any one of these to solve for the mole of water, either the concentration of the NaOH or the concentration of the HCl. And I'm going to show you why. So I'm going to do both actually. So the mole of NaOH, mole is equal to concentration times volume. The concentration of NaOH would have been 1.0 mole per dm cube. Volume of NaOH is 50 centimeters cube, which would be 0.050 dm cube. How I got this? 50 centimeters cube divided by 1000 would give us this answer. Right, that's how we work to find dm cube. Units will cancel, and so we get 0.05 mole of NaOH. Now to work out the mole of HCl, same thing. It's going to be concentration times volume is equal to the concentration of, it's not HCl, it's H2SO4, sulfuric acid. So the concentration that we would have gotten would have been 0.5 mole per dm cube, and the volume is 50 centimeters cube, which would be 0.050 dm cube. Right? And our answer, so let me just work that out. So it's 0.5 times 0.05, which gives us 0.025. Units cancel. Now if we were to write our balance equation, it would be NaOH, which is AQ, plus H2SO4 AQ to give, remember, base plus acid gives salt and water, right? So, and our water is quite easy for us to form. It's formed from the hydrogen and the hydroxide, so it's going to be H2O for the water. What remains is the SO4 and the Na, right? So it's going to be NaSO4. However, this is not correctly written because Na is in group 1, or Na would have a 1 plus charge, sulfate would have a 2 minus. When we drop our charges, it gives us Na2, see it drops, Na2SO4. So a 2 needs to be here for the correct chemical formula of sodium sulfate, salt that we formed. Alright, now to balance this equation, it's going to be, we have 1 Na here, 2 Na on this side. So to make that the same, we're going to put a 2 here. And we have 2 oxygen, 2 plus 4 give us 6 oxygen on the left, 4. Oh, I see what I'm doing. Alright, and so I'm going to leave the oxygen for last. Let me check other things such as my sulfate. We have 1 sulfate on our left, 1 on the right. We have 2 plus 2 hydrogens on the left, 2 hydrogen on the right. I just put a 2 here. Why I left the oxygen is because oxygen is usually the most difficult thing to solve for, and it's recommended that you balance oxygen last, and you realize that once you balance everything else, the oxygen will balance as well. Alright, so I put my 2 there, and now this equation, it is balanced. We have 4 hydrogen, 2 plus 2 is 4, and we have 6 oxygen, 6 oxygen. So it is balanced. Now, if we were to do the mole ratio, we'd see we have 2 mole of NaOH reacting with 1 mole of sulfuric acid. The mole of NaOH would have been 0.05 mole. Sulfuric acid is 0.025 mole. I'm gonna put a mole ratio for water. 2 mole of water is produced. Right? And if you were to look at it, this is what we want to know. If you were to look at it, you could see that since the mole of sulfuric acid, it's a 1 mole of sulfuric acid, right? And for every mole of sulfuric acid that is used, the mole of sodium hydroxide is doubled, right? So it's multiplied by 2. So hence, we have 0.025 here. If you were to multiply this by 2, you would get 0.05 mole of sodium hydroxide, just to simplify things, I'm gonna say that since I have a 2 mole ratio here, 2 to 2 mole ratio between my sodium hydroxide and my water, I am just simply going to say that the mole of water that is reacting will be 0.05 mole of water, since it's a 2 to 2 mole ratio. You could have used this to solve for water, which you would have just multiplied by 2, or you cross multiply. Right, I'm going to show you the cross multiplication version. So let's say you didn't work out the sodium hydroxide, but you did in fact work out the sulfuric acid. It's a 1 to 2 mole ratio, H2SO4, H2O. So 1 to 2 mole ratio, right? And we know that we had 0.025 mole of sulfuric acid reacting to give us X mole of water. Cross multiplying, I would get 1x, so this time this is 1x is equal to 2 times this, which would be 0.05 mole. So any way you work it out, you would get 0.05 mole of water. And now I am going to move on to calculate my heat of neutralization. So heat of neutralization, Q is equal to not Q, but triangle H of neutralization equal Q over -1 times mole. For Q, we would have gotten 2.814 kJ divided by the mole -1 times 0.05 mole of water. And our answer, 2.814 divided by 0.05, which gives us negative 56.28 kilojoules per mole. This negative suggests that my reaction is exothermic. The reaction is exothermic. And if you have looked at the question and realized that the temperature increased, and once again, once you see an increase in temperature, it means that the reaction is exothermic. And for the energy profile diagram, it's going to look something like this. Reactants are going to be higher than the products. And we would write our reactants on the left. So it would be our H2SO4, which is AQ, and reacting with our NaOH. Products formed Na2. Product formed with Na2SO4 plus water. The activation energy goes between the reactants and the products, so this would be my activation energy. Products between the reactants and the highest peak, the activation energy goes between the reactants and the highest peak, right? And then the enthalpy change goes between the reactants and the products, right? And that's going to be enthalpy change of neutralization, or heat of neutralization, equal negative 56.28 kJ per mole. And that's how we solve for our heat of neutralization. 5.35 grams of ammonium chloride in 100 centimeters cube of distilled water. This is the amount that we dissolve. The initial temperature of the water is 22.5 degrees Celsius. After mixing, a minimum temperature of 16.4 degrees Celsius is recorded by the student. Determine the heat of solution of ammonium chloride and draw the energy profile diagram. Okay, so we need to determine heat of solution. And from the equation, heat of solution is equal to Q over -1 times mole. And we are going to solve for Q first. Q is equal to mc delta T. M represents mass. M represents mass, and it's going to be the mass of the solvent. How I knew it was the mass of the solvent? Once you're doing heat of solution, we're trying to solve for heat of solution. You have to recall that for heat of solution, it's a heat change when 1 mole of a solute dissolves in a solvent. right? And the solvent is what accounts for, what gives the overall solution its weight. So we're going to use the mass of the solvent. Now note that for the solvent we were just given 100 centimeters cube of distilled water, right? It's given in volume. We get 100 centimeters cube of distilled water. Right, now we need to convert this to mass, and since we know that the density of water is 1 gram per centimeters cube, right, therefore 100 centimeters cube is going to be equal to 100 grams. Another way to work this out is that you could simply do 100 centimeters cube times 1 gram per centimeters cube. Units will cancel and you get 100 grams. So this would be the mass that we're going to use in the MC delta T. Just remember that for mass, when we're doing heat of solution, the mass that we use is the mass of the solvent. The solvent accounts for the mass, accounts for the weight of the substance, all right, or of the solution. C now, we're here. C is the specific heat capacity of water. This value is usually given. Sometimes you get it as 4.2, sometimes it's 4.18. Use whatever value you get. It's going to be 4.2 joules per gram per degree Celsius. So we have this value here, and this is our standard. Then it's the change in temperature, which is final temp minus initial temperature. Now in the question, note that it said an initial temperature of the water is 22.5 degrees Celsius. That's the initial temperature of the water. After mixing, a minimum temperature of 16.4 degrees Celsius is reached, right? And this is important. Note that it says a minimum temperature. So after we mix it, we get this minimum temperature. So this is going to be the final temperature that we use. Now, sometimes, let's say you get the values. I'm just going to draw up a little table. You get something like this. So this was the first initial. And then when they added the sodium, this is it. This is our water with an initial temperature of 22.4 degrees Celsius. And when they add the NaCl, the temperature begins to decrease. So it goes to 20, 18, 16.4. Then we realize that after some time it starts to increase. Alright. Now notice that yes, although this would be the final temperature, and I'm giving you this because sometimes in the exam they give you tables, right? Now notice that this would have been the final temperature, yes, but we're calculating, we're solving for the temperature change, and the temperature change would be the difference between, would be the actual difference between the highest and the lowest temperature. Now initially this was the temperature that we started with, this was the temperature of the water. But we realize that the lowest temperature, the minimum temperature reached, is this, right? So this is going to be our temperature change. Temperature change is going to be the difference between the initial and the minimum temperature, right? Notice that for here, after the 16, after you would have reached 16.4, what happens is that the reaction would have probably stopped, and then the temperature starts to increase once more. All right, so coming back down here, we have a final temperature of 16.4 degrees Celsius, initial 22.5 degrees Celsius, and we should get 6.1 degrees Celsius. And it's not just 6.1, it's going to be negative 6.1. And this is important for what we are about to do. All right, so we have solved for all of our MC delta T values. Now in the equation, we need to solve for the mole. And we're solving for the mole of the solute. Once again, the heat of solution is the heat change when 1 mole of a solute dissolves in a solvent. So we're calculating the mole of the solute, right? And it's going to be mole equal mass over molar mass. The mass that we were given of our ammonium chloride, that's our solute, it's 5.35 grams. The molar mass of ammonium chloride is 53.5 gram per mole. So therefore the mole is going to be 0.1 mole. That's our mole. Now we can solve for the enthalpy of solution. Is equal to MC delta T over -1 times mole. So we're going to put our mass. The mass is 100 grams. The specific heat capacity is 4.2 joules per gram per degree Celsius, and the temperature, the change in temperature is -6.1 degrees Celsius. My bad. And we divide this by -1 times the mole, which would have been 0.1 mole. When we put this in our calculator, we should get negative will cancel negative, and we get a positive 2000. Okay, this is going to be 25,620 joules per mole. Notice that the units will cancel mass, degrees Celsius cancel degrees Celsius, and we get joules per mole. Joules per mole. Right? Now to convert this to kilojoules per mole, you would divide it by 1,000. So we go 1, 2, 3, and so we get positive 25.620 kJ per mole. And that's our answer. Note that this is a positive enthalpy value, right? And hence we say that it is endothermic. Positive enthalpy value, hence it is endothermic. And that's the reason why I use this equation, just in case sometimes you don't remember that the temperature, as we can see, the temperature would have decreased, and once you see a decrease in temperature, it is endothermic. Now just in case you don't remember that it's endo, and endo will always give a positive value, we use this equation here. Alright, now we need to draw the energy profile diagram, and for endothermic reactions, we know that energy is being absorbed. And since energy is being absorbed, we're going to have our products having more energy than the starting reactants. So I'm going to have my reactants here and my products here. Drawing my little jump. Initially we had ammonium chloride plus water. Put those our reactants on the line. Reactants. Products. Once ammonium chloride is dissolved in water, it gets ionized, so it's going to be NH4 plus AQ plus Cl minus AQ. Alright, and now we need to draw in, let me just label my axes. So this is energy content. What is energy content on this axis? Low energy, high energy, energy content. This axis is going to be the progress of the reaction. So we're going from reactants to products. That's why it's a progress of the reaction. Now we need to include our activation energy. That's what we need to include. Right, and activation energy, remember, is the minimum amount of energy that the reactants need to break in order to form new bonds in the products, right? So for our reaction, the activation energy is going to go from the reactants to the top peak here, right? So this is my activation energy. And then for the enthalpy is the difference in energy between the reactants and the products. So the enthalpy change is going to be between the reactants and the products. So enthalpy change equal positive 25.620 kJ per mole. Here's another question. A student dissolves 10 grams of potassium nitrate in 100 centimeters cube of water. The initial temperature of the water is 25 degrees Celsius. After dissolving the potassium nitrate, the final temperature of the solution is 21.0 degrees Celsius. calculate the heat of solution for the potassium nitrate. Now before I get into this question, I want you to note two things. The difference between Q and the enthalpy. Now Q is the energy being absorbed or released, or it's just simply the energy content of the system. And why I'm giving you this is because sometimes they might ask you to solve for Q first and then solve for heat of solution or heat of neutralization. So Q would have just been the energy of the system, the energy, just energy, and Q is equal to MCAT. Now delta H, enthalpy, which can be at this level, can be enthalpy of solution or enthalpy of neutralization. Right? Enthalpy of solution or neutralization. And it is really just the heat change per mole. Heat change per mole of a substance. So just be on the lookout for these questions. If you're solving for Q, they usually ask you to solve for the energy content or the energy being absorbed or released. Remember that Q is equal to MC delta T. If you're solving for enthalpy, which is enthalpy of solution or enthalpy of neutralization, is the heat change per mole, and you must use enthalpy of solution or enthalpy of neutralization is equal to Q divided by -1 times mole. And oftentimes you're going to see the units. So if they want you to solve for Q, they're going to give you the unit joules. If they want you to solve for Q, if they want you to solve for enthalpy, they're going to give you the unit kilojoules per mole. So just be on the lookout for those two things. All right, now going back to our question. A student dissolves 10 grams of potassium nitrate in 100 centimeters cube of water. Okay, so the first thing that we're going to calculate, we're going to write out our entire formula. We need to solve for the heat of solution. You know that heat of solution is equal to Q over -1 times mole. That's heat of solution. All right, and now we're going to solve for Q first. Q is equal to MC delta T. M, once again, M is mass and it accounts for the weight of the substance. What accounts for the weight is the overall weight would have been the water. Alright, so it's going to be the mass of the water or the mass of solvent. So it's 100 centimeters cube times density times 1 gram per centimeters cube. This would give me 100 gram. Specific heat capacity is 4.2 joules per gram per degree Celsius. Change in temperature, final temp minus initial temp, which is equal to, see here, the initial temperature of the water is 25.0 degrees Celsius, and after dissolving, the final temperature is 21.0 degrees Celsius. The overall change in temperature is going to be -4 degrees Celsius. That's going to be our change in temperature. Alright, now we need to solve for mole. And it's going to be the mole of the solute, the substance that is being dissolved. In this case, mole is equal to mass over molar mass. And note that the solute that we're working with is the potassium nitrate, the substance being dissolved. The mass of potassium nitrate would have been 10.0 grams. The molar mass, can we recall the molar mass? Where the molar mass of potassium is 39.09. Nitrogen is 14 and oxygen is going to be 3 times 16. This gives us an overall answer of 101.10 grams per mole. Right, and we're going to put it here. So now we need to work this out. So it's going to be 10 be 10 divided by 101.10. That gives us a mole of 0.0989 mole. So our answer there. Now we need to go ahead and solve for our heat of solution. Q over -1 times mole. Q, which is MCAT, is going to be 100 grams times 4.2 joules per gram per degree Celsius times the changing temperature, which is -4 degrees Celsius, divided by -1 times 0.0989 mole. And now you work. So it's going to be 100 grams times multiplied by 4.2 multiplied by -4. This gives us -1680 divided by -1 times this gives us -0.0989 mole. Note that the unit for the top, mass cancel mass, degree Celsius cancels degree Celsius, and we are left with joules, right? When we have two negatives, one being divided by the other, we would get a positive sign. So it's going to be 1680 divided by 0.0989. That gives us an answer of 16,986.9 joules per mole. And to convert this to kilojoules per mole, it's going to be divided by 1,000. This gives us the answer of positive 16.9869 kg per mole. And that is it for this question. Just to do a little addition of the energy profile diagram that we're going to be working with. Since it is a positive enthalpy value, we know that positive enthalpy values are endothermic, right? So therefore, for endothermic reaction, heat is being absorbed, right? Heat is being absorbed for endothermic. So therefore, the products are going to have higher temperature than the reactants. So I'm going to have my reactants having not higher temperature, sorry, higher energy than the reactants. So this is going to look something like this, with our potassium nitrate and our water being on the reactant side. And for the product side, it is going to be, once you have something being dissolved in water, it gets ionized. So it's going to be K plus NO3 minus, both in their aqueous state since they were dissolved in water. Alright, this axis, energy contents, and this axis is going to be the progress of the reaction. And once again, to include our activation energy, is going to go from the reactants to the top peak. That's activation energy, EA, and our enthalpy change goes between the reactants and the products. So it's going to be between here, equal positive 16.9869. Just to recap, just remember that for enthalpy of solution, it's a heat change when 1 mole of a solute dissolves in a solvent. The way we calculate it is enthalpy of solution is equal to Q over -1 times mole. And for the Q is equal to MC delta T, where the M means the mass of the solvent and the mole is the mole of the solute. Right, and just to recap as well, for the enthalpy of neutralization, that's the heat change when we form 1 mole of water after the reaction of an acid and a base, right? And for the calculation of enthalpy of neutralization, it's still Q, it's still enthalpy of neutralization is equal to Q over -1 times mole, where Q is equal to MC delta T. Right? And in the case of enthalpy of neutralization, the M, the mass, is going to be the total mass of the solution, and the mole is going to be the mole of the water that is formed. Alright, so that's it for this video. Thank you for watching. That's it with Miss Wallace Teaches Chemistry.